Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the University of Helsinki, where I get to study fun things happening inside the universe. So yeah, I'm a cosmologist, I study the universe, the contents of the universe, how everything evolves, how everything interacts, and I love chatting about the universe with everybody. This is why I'm here live on Cup of Cosmology over on HAPS. We should also be going live out to Twitter, to Twitch and to YouTube and maybe to Reddit, wherever you're watching from. Welcome. It's great to have you here. Hey, Ange, really, really nice to see you. Thank you for joining, as always. So today I'm really happy that I have a guest joining me. Haven't had a guest on HAPS in a while, so if anything goes wrong, it's completely on me and still getting ready with all the technicalities, but I'm really, really happy to have a guest with me today, and I'm going to bring her on screen and let her introduce herself. You should be coming on in 3, 2, 1. Okay, let's see. Hi, Anna, and welcome to Cup of Cosmology.
Hello, nice to
Great.
be here.
Yeah. Just seeing some people in the comments. Hey, Paul. Hey, David. Hey, Scott. Great to see you all. Always, always nice to see everybody here in the comments. So, Anna, do you want to introduce yourself to everyone?
Yes, so I'm a PhD student at the University of Helsinki, Finland, and I study the very first second of the universe. And I basically focus on gravitational waves and all sorts of fun stuff that happens during the very first second.
It sounds like 1 second. What could possibly happen in 1 second? But really, a lot of people,
A
a
lot.
lot of stuff can happen in 1 second. There is so much that can happen. How do you add people into the stream? I am live on HAPS. HAPS has this feature where I can just bring anybody in the world up on screen with me. I think I'm allowed up to a maximum of 3 guests currently. So thank you for joining over from Reddit. Great to see you. Glad to know we're going out to Reddit as well today. Always, always good to see that. So, two people in Helsinki, indeed, we are actually colleagues. In days when we're allowed to the office, we do actually work in the same building and enjoy coffee breaks together. So, yes, we are indeed in the same group here. So, lots of people in the comments here saying hello. I guess you can see the comments as well, Anna. They should be on
I
the
can
right
see
hand
the
side.
comments, yes. Hello, everyone.
Perfect. Glad you can see it. So we already have a great question here. Is the first second an oxymoron? You're going to have to get used to bad jokes from Scott. It's just a default in this stream. Okay, so you mentioned you study the first second of the universe. You want to elaborate a bit, like why do we care so much about the first second? What do you do about the first
So
seconds?
I specifically currently focus on the let's say 1 picosecond after, or roughly 1 picosecond after the Big Bang, where the Electroweak phase transition happens. So we have 4 basic interactions in the nature. So we have the gravitational, weak, strong, and electromagnetic force. So the Electroweak phase transition is when the electromagnetic and the weak force become separate, and that is the point that I'm interested in because all the cool, exciting physics that can happen at that moment.
Yeah,
That can lead into gravitational waves. There's also cosmic strings that can form during these phase transitions, and yeah.
awesome. That's a very nice introduction. So just want to say to everyone, we're dropping a lot of buzzwords here: cosmic strings, phase transitions, gravitational waves. Don't worry, we're going to elaborate on all of these things throughout the stream. But as always, this is an interactive stream. The idea here is that you can ask anything you want. So Anna and I are going to try to do our best to answer any questions you have. Today we're focusing on this first second of the universe, this very, very early times in the universe. Any questions you have, keep them coming. Whichever platform you're watching on, we will see all of your comments coming in here on HAPS. So do keep your questions coming. We will do our best to answer all of your questions. If you people don't have too many new questions, then I get to ask Anna questions, and maybe Anna would prefer you people to have questions. So we already have a first question over from David on Reddit. We talk about this first picosecond. Is this during the Big Bang or after the Big Bang?
After the Big Bang, we cannot know what happens before or during the Big Bang. So it is definitely after.
Yeah, everything we discuss here is always going to be after the Big Bang, because the Big Bang is just the start where we start all our equations. Hey, Peter, great to see you. Haven't seen you in my streams in a while. Really, really nice to see you here, Peter, as always. So yeah, anything we talk about in the early universe is always going to be after the Big Bang, because by definition, we can't know anything that happened during the Big Bang or before the Big Bang. So everything we're talking about is from the Big Bang going forwards. So we already have a really nice question here from Paul over on Hats about the forces. So maybe we can just elaborate about these 4 forces in the universe. Like, what do each of them do? Because people might be used to hearing about the gravitational force. Some of us are used to electromagnetic, but strong and weak force. Can you just give a brief summary of what all the 4 forces are?
So gravitational is, of course, you can stand on the Earth, and there's something pulling you towards the Earth. But it is a very weak force. You can easily overcome it, but it's a very large scale force in that sense that it affects all the planets that orbit around the sun and so on. Well, electromagnetic force is, for example, electricity, anything like that in your daily life. And then weak and strong is something that I usually couple in the same category of atomic scale physics, also subatomic scale physics that do fun stuff.
Yeah, the way I usually describe it, strong force is the one that holds everything together in the early universe, and weak force is the one responsible for things like radioactive decay. And that's a hand-wavy explanation we all give, because we either give a super mathematical explanation of the weak force, or we just throw out radioactive decay and move on. And that's absolutely what we're doing. And I see a few people are asking us to clarify here what we mean by picosecond. So for those who don't know what a picosecond is, that's perfectly fine. It's a very technical word. Picosecond means 10 to the minus 12 seconds. So that's 0.11 zeros and a 1. That's how much of a second it is. So it's a 1,000th millionth of a second. So it's really a tiny, tiny, tiny fraction of time. So the question we had from Paul about the forces here, were both forces, the electromagnetic and the weak, always there doing the same thing, or did a new force come into being at the time when we have this phase transition? So they were united, they separated. What does this mean?
I mean, at the phase transition, they just become separate. They have been unified into a one singular force before that. And then when they reach that certain second after the Big Bang, or fraction of a second after the Big Bang, they just become separate. So they are the 2 distinct forces after that, but you can't tell them apart before that, is the short answer.
Yeah, so we think in the early universe that all of the forces were united at some point and they gradually separated. We started with all of them together and they gradually broke into the 4 that we have today. So we know for sure that we had this electroweak phase transition when the electromagnetic and the weak forces were combined and they split. Now, in order to put the strong force together, we need to go earlier back in time. The reason for this is we need high energies to unite these forces. The earlier you go back in time in the universe, the higher the energy. So at even earlier times in the universe, we think the strong force was united with the electroweak. Now, to explain this, we need the grand unified theory, which we're still trying to figure out. And then even further back in time, it might have been that gravity was also united and we had one force to rule them all, kind of Lord of the Rings style. And for that, we would need the theory of everything, which we're also still working on. So if you've heard of theory of everything and grand unified theory, it's basically trying to put all of the forces together. But the one we do know for sure is the electroweak phase transition, that the electroweak forces were together and at some point they split up. There's a nice comment here also from David on Reddit. Is this cosmological second or second in relation to the Earth? This is a great question. And when we're talking about times in the universe, we do take 1 second, 1 Earth second or 1 Earth minute as our reference. But of course, there is the thing that however fast you're moving in the universe, the definition of time changes. But when we try to talk about the history of the universe, it's useful to have a system that we're familiar with and that we understand. So we really are talking about 1 Earth second here. So I always say, Anna, here, if I say something wrong or if you want to elaborate on anything I'm saying, do feel free to jump in at any point. Don't worry about interrupting me. Just jump in if I say something you disagree
Yes, of
with.
course.
Okay, so we mentioned that we have this electroweak phase transition. So how do we know that these forces were united? I'm throwing hard questions at you, I know.
Actually, I'm not sure about the answer to this one, so I'm going to leave you to answer this one.
Yeah, I mean, how do we know? It's a good question. I was hoping you could answer that. Sorry about that. So, based on a lot of our understanding of the standard model of particle physics, it seems like these forces had to be together. Now, of course, we would like to find evidence of this electroweak breaking that would show us that this definitely happened. This we can tie directly into something else that Anna mentioned, which are gravitational waves. So why would gravitational waves from the phase transition be important? Why would the phase transition produce gravitational waves? I know these are two big questions. So what do you think, Anna? Do you want to tie together gravitational waves and the phase transition?
So, well, there are multiple things that can happen, of course, during the phase transition. So, are we talking now about more generally speaking, like cosmic strings type of thing, or do you want me to specifically go through the Electroweak phase transition? is kind of the question here.
Yeah, it's kind of the question. I think where I'm aiming at with the question is why would electroweak be so what is the connection between electroweak phase transition and gravitational waves? And you can get the connection however you want to explain it.
Yeah, so let's see where I should start. So we know phase transitions, in our daily lives, right? Everyone has seen water freeze into ice. So this electroweak phase transition is basically just like a cosmological equivalent of that. It's slightly more complicated, of course. You can't just can't quite reference the ice freezing into water, but it's the same principle still applies. So in this electroweak phase transition, the universe has basically two phases. So there is something called a false vacuum phase and a true vacuum phase. So we have water and ice, or liquid and frozen water, essentially. So here the universe starts at some critical temperature. So universe is like this hot plasma soup at first, right? And then the temperature starts to go gradually down. And eventually it will hit some critical temperature where um, where there are now two phases that can exist. So there is this true vacuum and false vacuum phases, and the universe can get kind of trapped in the false vacuum state. And like bubbles in a soup, for example, or in a boiling water, you get these like bubbles of the true vacuum eventually, because one part of the universe has no way of kind of knowing that some other part of the universe has kind of settled um, in the true vacuum state. So you get these like areas of expanding true vacuum states, like bubbles expanding, and these bubbles then colliding as they expand is what causes gravitational waves, basically, to be created at these like collisions of these bubbles. And this is something that may still be detectable even today, even though they have originated in such a long time ago. But it was such a violent kind of event in a sense that we could still hopefully detect these gravitational waves in the future. And why we haven't yet detected them is because the frequency of these waves is like LIGO, if you have heard of LIGO, which is a like a big gravitational wave detector on Earth, for example, hasn't seen anything, is because the frequency range of these early universe gravitational waves is kind of on the wrong um, frequency. So LIGO can't hear them,
So,
essentially.
so I do want to say that's a very nice answer. And for anyone watching, I did throw a really tough question at Anna there, like basically explain everything you've ever worked on in a few minutes. So that was a big question that I threw at you, and I think you did a really good job answering that. We have a comment from Scott here when you were talking about these bubbles, asking, are these like nucleation points?
Yes, essentially, this is like a nucleation of bubbles that we are interested in, and um, how fast they first of all move, and all sorts of stuff.
So we do have a question here from someone on Reddit. Why are you talking about things you'll never see for yourself? And I want to take that question. And first of all, I want to mention that we are both theoretical physicists, and talking about stuff we'll never see is basically what we do our entire lives. But the thing is, we might actually be able to see this. So as Anna was just explaining, if we had this phase transition in the early universe, it could have been so dramatic that it left ripples in the fabric of space-time. So it left these tiny gravitational waves imprinted on the fabric of space-time. So if we were able to measure these ripples today, It would help us understand how this phase transition happened. So it's not things that we might never see for ourselves. We might actually see this. This is something that we can hope to measure in the future. And it's kind of incredible if you think about it. We're going to look for tiny, tiny ripples in the universe itself to try to understand the phase transition that happened 13.82 billion years ago. It's ridiculous when you think about it. Just want to go into what Anna was saying a bit more here. We have gravitational waves from the Ligo detector, but these are bigger. So anyone who's heard me talk about gravitational waves, I say they're tiny. If two black holes smash together, you get ripples in the fabric of space-time, but these are so tiny that if one hit you, you'd grow by a millionth the width of a human hair. And now, when we're talking about these early universe gravitational waves, we're talking about something that is millions of times smaller, which makes it really, really, really difficult to detect these things. But if we do detect them, it will tell us so much. I saw there are... Sorry, go ahead.
Sorry. I do also feel that I should point out that in the standard model of particle physics, so what we so far is the best theory of physics that we know of, but we also know that it's not the full story because it doesn't explain dark matter and so on. So this standard model of particle physics, so where you have all the particles such as electrons and the Higgs boson that was discovered in 2012, I believe. Diana, please correct me if I'm wrong now. I'm bad with years. So in the standard model, the Electroweak phase transition is not necessarily actually... It's something that we call a crossover, which is not really a phase transition in like the physics kind of sense. And that might not actually create gravitational waves. But in this beyond the standard model theory, so we take this standard model and then we add something to it. In these theories, the Electroweak phase transition is quite common, and that is the reason why there is research ongoing on it. So.
Yeah, so the image that I put up on the screen, depending which platform you're watching on, it's either above or to my left, I believe. I think on one platform it might even be to my right because I like moving it around. But this image that you can see up here is our standard model of particle physics. And here we have all of the known building blocks of the visible matter in the universe. So I just want to mention that this does not include dark matter or dark energy. But this is what we know. This tells us all of the Lego pieces we have to build our universe and how they fit together. Now, as Anna was saying, within everything we know about the standard model, this electroweak phase transition would actually not produce gravitational waves. But if there's a missing piece in our standard model, and there's a lot of reasons to think there might be missing pieces in the standard model, then we could have these gravitational waves. So this means that if we ever measure these gravitational waves and we can tie it specifically to a phase transition, it's evidence of new physics. It would be hints of something that we need beyond the standard model. There's a few questions we missed here. Just to comment to anybody who's new here, we do try to get to all of the questions. Sometimes it might take a while. So if we ignore your question the first time, please know that we're not deliberately ignoring you. Just sometimes we get carried away, and we will try to get to the questions eventually. There's a very nice question from Paul here, talking about these expanding bubbles in the early universe. If there were these expanding bubbles of a true vacuum state during the first second, would they have taken over the entire universe by now?
Yes.
So
they would gradually convert the universe into the true vacuum state.
So I can make a comment here. People who have watched my streams often might have heard me talk about the vacuum death of the universe, which is great fun. It's basically the universe wiping you out. And the principle behind it could be the same, where you have one bubble with a different property, and this gradually expands and wipes out everything in its path. Fun topics, but let's not get too catastrophic today. There's a question here, a bit off topic, of how do you think the universe began? I want to take this question a moment and say that actually we don't know. This is very important because a lot of people say the Big Bang was the beginning of the universe, and we do not know this. It was not big and nothing bang, that's an aside point, but we start our equations a fraction of a second after some initial event, after some initial singularity, which is just a fancy word of saying our equations don't work. So we start our equations a fraction of a second after this, and we move forward with it. Anything that came before, we can't really discuss from a physical point of view. There's also the thing that we believe time began with the Big Bang. So asking what came before time is something that doesn't really make sense to discuss. So we can't answer that question of how did the universe begin from a purely physical point of view. So we don't. There is no theory of physics that says this is what started the universe. There are a few models, there are a few hypotheses, but it's not something we can really answer from a completely scientific perspective because our equations don't work at that point. Hope that answers the question. If you have a different opinion at any point, Anna, do let us know.
Oh, I will.
So there's the question coming in from Reddit. How can you verify you're right if you'll never see it? So this is what we're saying. Like we might see it. We might see these cosmic strings. These gravitational waves. We haven't got into cosmic strings yet. So maybe we can answer the question here of if we find gravitational waves. I'm going to go back to LISA in a minute, the spacecraft you mentioned. But say in the future we find gravitational waves in the universe. These primordial early gravitational waves, so not the ones coming from black holes. How would we tell if that is coming from a phase transition or from anything else in the universe?
So basically, the idea is that each of these events in the early universe, they produce kind of like a spectrum of some sort. So you have like these signals from, for example, merging black holes or something like that. But from these early universe gravitational waves, you would get something more like continuous spectrum that we then try to model with computer simulations. So in order to know what would it look like, where would we roughly expect it to be based on the simulations that we can do, and then of course hope that the upcoming LISA mission that I suppose we should talk about at some point a bit more will detect some of these. So I would say maybe that the gravitational wave spectrum from these is somewhat comparable to CMB. You can disagree, Diana, with me on this.
No, but if you mention CMB, my regulars know what I have to do. There's an ongoing joke that I'm incapable of spending a single stream without flashing a specific image on screen. So if you mention CMB, I'm just going to take the chance to flash the image. And I do agree with everything you said. So I just had to do that gratuitous flashing of the CMB there. So this is actually the question that I asked you of how do we like disentangle these different signals is actually something that a lot of people in our group we're working on, is answering this question of how come, if we find something in the future, how can we tell where it came from? What type of studies can we do? What will this tell us about the early universe? The idea is to have the framework ready that if we get this signal in the future, we'll be able to directly say, okay, we already have a catalogue of what this could and couldn't be. And this is what they did with the Ligo one as well, where we had these black holes smashing together. Physicists had built up a catalogue for hundreds of years of all the possible signals we could expect. And then when you actually find the signal, you compare it to your catalogue and say, okay, this is two black holes smashing together. I just want to say hello to Anne here in the comments. I didn't acknowledge you when you came in. Great to see you, Anne. If anyone loves cooking shows, you should absolutely follow Anne Rush here on HAPS. She does some amazing looking food here. Always makes me hungry. To answer the question of how do you find us on Reddit, we are on the HAPS News subreddit. So if you go to HAPS News on Reddit, you can find a bunch of live streams. And currently we should be there as well. So there's a slightly off-topic question here, but that I think is fun. Is there any one event, like a supernova or a quasar or something else, that can form a singular event that mimics the experience of the Big Bang? So any event in the universe that is similar to a Big Bang. What do you think, Anna? Tough question.
I would say no. Just from out the top of my head, I would say no. But
I completely agree that no is the reasonable answer.
Yes.
We can ask fun questions like what happens inside a black hole. We don't know, but we do talk about black holes as singularities. And I want to emphasize here that a black hole singularity is not the same as the Big Bang singularity, even though they both contain the word singularity. But singularity, again, just means this is where our equations stop working. So we can't study exactly what happens inside the black hole the same way as we can't study the early universe when we have this word singularity, but that doesn't necessarily mean it's the same thing. Now, the problem with mimicking the Big Bang is the amount of energy involved. So the Big Bang was extremely high energy moment. It's the most energetic part of the universe we can conceive of. And even events like supernova, which are ridiculously energetic, don't come close to the energy you would need in the fraction of a time that you need for this initial singularity. So yeah, we don't think we can mimic the Big Bang in the universe, which is kind of difficult because then how do we study it if we can't, go in a lab and make it happen? So it's probably good that we can't set off many Big Bangs in our lab. It's probably for the
It would
better.
be a bit concerning.
Yeah, it's like, let me just go build a baby universe here. Maybe that's where the Sims game comes from.
Possibly.
Okay, so we've mentioned LISA a few times, the laser interferometer space antenna. Maybe we should discuss what LISA is, what it's going to do. Do you want to give us an introduction as to what LISA is?
So LISA, or laser
LISA,
interferometer
yes,
space antenna, it is
exactly.
like a space triangle, what I essentially usually call it. So it's three spacecraft that form a triangle, and then they orbit behind the Earth, or orbit the Sun behind the Earth, so it trails behind the Earth, and it has lasers passing between the three different spacecraft, and these lasers can then measure like the travel time of the light changes when a gravitational wave is passing by. So that how we know that a gravitational wave might have passed. So there you can actually, I think, is it up?
Should be
Up above,
up or
you
to the
can
left,
see,
depending where you're watching.
yeah, a quick visualization of LISA trailing behind the Earth. I believe it's 20 degrees behind the Earth exactly. The arm length of this thing, so the distance between one spacecraft to the other spacecraft, is, we call that an arm. Like with LIGO, we have two arms, so LISA has three arms. So the arm length of LISA is 2.5 million kilometers. So that is roughly 6 to 7 times the distance from Earth to Moon. So it's a huge distance. And this is hopefully launching into space in the early 2030s, hopefully. Fingers crossed that happens.
Hopefully, yeah, it's like less than 15 years away by now. Just want to mention that this really cool illustration that I'm showing here was actually made by Anna. Anna, do you want to tell us a bit about how you made this illustration, what it is, and where people can find it? Because it's really cool.
Yes, so this is a video on my YouTube channel, which is only has this one video currently. It's called Cosmo Blend, and on my free time, I usually toy around with Blender, which is a 3D visualization program. And this visualization here is created with Blender. So I have taken the approximate orbits of LISA and plugged them in to a code that then runs and updates where the location of each spacecraft should be. And then I have added some, well, materials and nice stars around it. So you can have LISA orbiting the sun in space.
Yeah, and I think this is really cool. Anna is being very nonchalant about this, but it's awesome that, this is now my default animation to show anytime we're talking about this spacecraft because it is really, really, really cool animation. Cosmo Blend sounds like awesome coffee. Yeah, it does actually.
It
It
does,
does.
yes. Huge thanks to my friend who came up with the name.
It is a very good name. There's a lot of people in the comments here saying that it's a very cool animation. Hey, David Howden, great to see you. Really, really nice to have you join the stream, as always. Let me see how I now get rid of that image. I'm still getting used to bringing things up and off of screen, so that should make it go away now. Yeah, so just want to emphasize this because it's really, really cool. This is three spacecrafts, basically, that we're going to send to space to the quietest part of the universe, which is just quite fancy because we can say the quietest place in space. But it's going to be, as Anna said, chasing the Earth as we move around the sun. With a series of lasers, it's going to measure ripples in the fabric of space-time created by things that happened thousands and millions of years ago. It's really cool when you think about it. And you know, in order to do this, we have to have something that's held basically in suspension in all three spacecrafts with perfect precision because we want to measure any differences in the arm, so any differences in the distance between the two out of the three spacecrafts. With three of them, we actually have like 6 legs that we can use. And well, 3, but they go in both directions, so 6, in case people are wondering where the number
Yes.
6 came from.
So there's two lasers between each arms, one outgoing and one ingoing. And unlike in the animation, the lasers you can't actually obviously see. like red lines or arms stretching in space. So
Yeah, in all of the animations, we have this kind of Star Wars pew pew effect of all of the lasers. That is not realistic, unfortunately. Also, lasers don't make that noise, but that's a whole other
I
thing.
kind of wish they did.
Would be cool if they did, right?
They
But
should.
they should. They should. We should make lasers with sound effects just because. So yeah, they're going to be bouncing these lasers back and forth between the spacecrafts. And in order to measure if there's any change in the lengths, they need this object suspended in perfect position. We need to measure its position perfectly. The engineering behind the LISA mission is incredible.
It is
And
truly incredible.
yeah, and this was proposed, I believe, already like 30 years ago, and it's really taken a long time to get where it is. It is now really developing. We should mention that it is an ESA-funded mission, also with collaboration from NASA, I believe. Correct me if I'm
Yes, it
wrong
is.
there. Yeah, so this is a really cool thing that's going to launch hopefully within the next 15 years. And just want to say that the day that launches, I will be a complete and utter wreck. Like, do not speak to me on that day.
I think it will be worse when they finally get the first results
Yes, yes.
in.
So maybe we can go slightly off topic here, off of the early universe gravitational waves that we like, because LISA is also going to measure other things. What other type of things is LISA going to measure for us?
I believe there's. Is it massive or supermassive black holes? How does the
Super,
classification go
I
here?
think supermassive black holes should be supermassive,
Possibly.
right? Oh, we should really know this.
Yeah,
Yeah,
I
I
found it
took us
from the
down an avenue
cosmological
there.
sources, not the
Yeah,
astrophysical ones.
yeah, the ones that produce smaller gravitational waves. Yeah, I believe supermassive black holes should be there. And also galactic binaries, so places where you have a galactic binary, so binaries within our galaxy. There's a few other things that it's going to measure, and I really shouldn't have asked that question without my cheat sheet ready.
Yes.
Yes, yes. But yeah, it's going to measure a lot of other things as well. So, one big issue that we have is trying to clean out, from our perspective, if we're trying to measure these early universe gravitational waves, we need to clean out all of the astrophysics, all of the things that can produce other signals that might get in our way. This is the thing when you have a spacecraft that can measure multiple different things, is going back to the idea of how do we break them up? How do we know if this signal came from A or from B? And that is what a lot of people are working on these days. We do have a comment here from David Howden when we said six lasers and six legs. That basically makes it an insect, and I like that. LISA is now officially an insect. Hey, Robert, great to see you. Thank you for being here. And David, I will be more stressed when LISA launches, because when the Just Wonderful Space Telescope launch, it's a cool mission, but I don't have anything involved in it. But LISA, like, so we're working on this, not directly, we're not building the spacecraft, but what we're doing is relevant. If that mission blows up when it launches,
That would be terrible.
let's
All of
just
my PhD work gone.
right, yeah, so that's not going to happen. We're definitely not already stressing about that 15 years ahead of time.
Yeah, thankfully there was the LISA Pathfinder mission already in
Yes,
2015, if I remember correctly,
2015.
which was successful, so
Yeah,
at least there is some hope that
yeah.
everything
So
will be all right in the end.
we already know that this technology works, that what we're doing makes sense, and that it is feasible. The biggest question is, are we going to pull it off? And that's always the problem with a space-based mission, right? Especially one that's so far away. It's, yeah, kind of difficult, but we have complete and utter faith in the engineering team and in everyone involved in the mission. We will not be at all stressed when we launch them. Another very off-topic question coming in from Reddit, but that I like. If you had an unlimited budget to conduct any experiment you wanted, what one experiment would you conduct?
Oh no, I'm not sure if I have a quick answer for that. Diana, do you want to go first?
So for me, the clear answer to that would be a detector for spectral distortions. So spectral distortions are tiny, tiny, tiny fluctuations in the perfect black body of the CMB, and it's a treasure trove of information. Within the standard model of cosmology, we expect there to be a signal. If we don't measure that signal, something's wrong. In many, many extensions to cosmology, like if you add decaying dark matter, if you have evaporating primordial black holes, you have these spectral distortions. it's a signal that is there. It's a test of lambda CDM. We just haven't had a mission. We had one mission, the Corbifidos mission 26 years ago, and it was great. It was did an amazing thing, but it was not precise enough to measure what we think is there. So for me, without doubt, it would be a spectral distortion mission. Assuming this doesn't take money away from things like LISA, of course, this is just different mission. I would absolutely go for a spectral distortion mission. Did you come up with an answer, Anna?
I'm not sure if I did. There's so many cool things, and I'm trying to think. There's all, well, for example, the pulsar timing arrays, they already exist.
Yes.
But I guess I could, dump that sum of money towards them and be like, please build more telescopes.
Definitely. I do like David Dunn's answer here. If we should just build a TARDIS, and if you figure out how to make it travel through space and time, count me in.
Yes.
But I think that's the problem, that we could build the box. We'd have a problem making it bigger on the inside, and we'd have a problem getting it to actually move through space and time. Well, making it move through space is a bit easier. Making it move through time, that's where things get tricky.
No, that's a bit challenging, yeah.
Yeah, we're still working on that one. Okay, so we mentioned early on, and we've mentioned a few times, we dropped this word of cosmic strings. Do you want to tell us what are cosmic strings? Because this is something you have worked on.
Yes, I have worked on this during my bachelor's degree, so it has been a while. But so cosmic strings, there's this nice thing that people usually use when they try to explain them. So imagine a lake and it starts to freeze. So you have these patches of ice floating about that don't know about each other. And obviously, as the lake continues to freeze, these patches of ice eventually will collide with it. Well, not collide, but come into contact with each other. And you get these fractures. You see, when you look at ice, you have these like fractures kind of in the ice when it has like frozen and become solid. So cosmic strings are kind of these like defects that you can also see in ice. So I've already mentioned this like phase transition and symmetry breaking. So it is a bit similar here. So you have a symmetry that breaks. So you, for example, have the phase transition where you break from the Electroweak force down to the separate forces. So, for example, that kind of phase transition or something similar to that, where you eventually, if you could, Diana, bring up the image again that you already showed.
Yep, I was waiting to see when you would need it, because I brought it up a bit too early before. Yeah. Sorry about that. Here we go.
So the idea is that when you, for example, have the Higgs field, that gives things mass. So you can kind of fall. So you have this like potential that looks like a hat. Okay, that's the Higgs potential. You have a nice hat, and then you fall from the top configuration. I believe I also sent that to you, Diana, if you can bring that up.
Bringing it up. We can only have one at a time, so
yeah, okay, thank you. So you have this, it looks like a hat, right? So you are
Mexican
in this
hats.
like, Mexican hat. So you have this Mexican hat potential, so you are on the topmost configuration, and then you can fall down from there. And now the orientation where you are on the hat basically gives a direction to the Higgs field, which then results in the sense that, like the ice patches forming, you have now different patches that have slightly different orientation in the universe, because they are so far from each other that the universe doesn't know that some parts of it have already fallen somewhere. So when it connects, like the ice sheets eventually have to connect, it has to pass through this like peak orientation that you see on the figure, hopefully. So it has to go through that peak in order to work, like the ice sheets. So we call that like the high energy kind of structure, and that is the ice fracture that you see, or in our case we call that a cosmic string. So a cosmic string is like a line-like defect in the universe that is like a really long string, basically stretching from one edge of the universe to the other edge of the universe. It is very dense, but very, very thin.
Yeah,
And
they're often referred to as like these one-dimensional massive strings in the
yes,
universe.
yes, and this doesn't necessarily, or in generally speaking, it doesn't have anything to do with string theory. No, despite the name, that can be a bit confusing. But there are something called cosmic superstrings that then I think kinda can relate to string theory. But so the answer is yes and no, but mostly no. It doesn't have anything to do with string theory.
Yeah, if you have these superstrings, which would be much, much bigger, you can relate them to string theory. But initially, they're different concepts. Yeah, we do like throwing strings about and everything.
Yes.
And I do love the cool images. Did you make these images? I love the rainbow images.
Yes, I did. I believe I made them for my bachelor's thesis at the time.
They are very, very nice. So what was I got distracted when you talked about two ice sheets hitting each other because I've been freaking out for the last few days about the fact that the sea is frozen in Helsinki, and I know you all keep saying like this is normal. It is not normal. I'm freaking out.
It
I
is
actually went to
completely normal.
no. I went to see yesterday. I went to the beach to the sea, and it is completely frozen. There were people skiing on the sea. No, I'm not going to stop freaking out about that. You distracted me when you're talking about the ice plates because anyway, Helsinki is a magical place.
Happens every
So
year.
yeah, that doesn't make it any less magical. The fact that this happens every year and you all just climb about it. No. I love it. But yes, I was freaking out about that. So
And also, it indeed is frozen.
yeah, you can walk on it. You can walk on the frozen sea. There were footprints of people walking on the snow on the sea. Insane. There's no way I'm doing that. I don't trust myself enough on non-frozen places. Uh, okay, got a bit distracted there. Someone's asking, someone who joined late, are you from Finland? So do you want to just, again, for anybody who joined late, do you want to just briefly introduce yourself again?
Yes, so I'm a PhD student at the University of Helsinki, and I am now doing this is my second year of my PhD, and I study the very first second of the universe.
All of the cool
Mainly, I
things we've been talking
focus
about.
on those like gravitational waves from phase transitions that we already talked about, and working on the LISA mission, like the trying to get the gravitational wave spectrum looking correctly and stuff like that. So I'm kind of part of the analysis pipeline for that. And I have also worked on cosmic strings. They are a bit complicated to explain, so hopefully people usually use that like frozen ice sheet analogy. So
Yeah.
hopefully that works somewhat.
Yes. So as always, if anything's not clear, do let us know here in the comments, and
Yes.
we'll try to explain. We'll try to elaborate. So just to bring everything together, bring it back on track, because I got distracted with the ice. These cosmic strings are structures that could form in the very early universe, one-dimensional, could be very, very big, and then there's a cool question of what's the connection between cosmic strings and gravitational waves.
So also I should probably answer yes, I am from Finland. But so basically these strings, so they are very, very long. However, they can kind of like we call it intercommuting, which essentially means that they can tangle with each other and chop off a smaller loop, or they can tangle with with just like other
With
strings
themselves.
and chop off like smaller loops. And these loops can then, because they kind of wiggle and oscillate, they can then radiate gravitational waves, which is also how cosmic strings decay. So these gravitational waves from these like decaying or decayed cosmic strings are something that we could detect again with LISA or with these pulsar timing arrays that I think I briefly mentioned already. So these pulsar timing arrays, they are just like millisecond pulsars that are scattered across the sky, and they have a very stable kind of a pulse period. So when they shine light towards the Earth, and we can see that and we can measure the time from there. So if a gravitational wave would pass through these pulsars, or pass through these pulsars, or they would see them because we would then time the arrival time from the pulsar, the light's arrival time, and we could see that, okay, something has happened there based on the timing. That's why it's called pulsar timing arrays. And you don't just need one of these, you need many of these, so you have like an array in the sky. And there's Nanograv that is part of there's like a big collaboration. There's the I believe North American one that is Nanograv. Then there is also, I believe, Australian one, if I'm not mistaken. And there's one third, but I can't remember right now. Is it the Europe? It's not the European one, is it?
I have very limited knowledge about pulsar timing arrays. It's on my
Okay.
list of topics to look into for a future stream.
Yeah, but there is a whole collaboration, and there has been, I think, Nanograv releases the data from the observation runs, and I think there was recently a big paper about it, but I haven't actually read it. Too many things to do.
There's always so many things to do, always. But yeah, I mean, this is pretty cool. We're using pulsars, which are kind of like lighthouses of the universe, to try to measure gravitational waves. And human ingenuity will never fail to amaze me. We're coming up with all of these crazy ways to measure gravitational waves. So yeah, we can have these cosmic strings in the early universe. If they bend over and form kinks or cusps, if they smash into each other, a loop can break off. As Anna said, this loop would then decay. This would produce gravitational waves, which we could hope to measure today. Now, there's a big question of, have we ever found cosmic strings? And I'm going to answer that one myself first, but of course, feel free to jump in. The thing is, cosmic strings would actually leave an imprint that would be measurable on the CMB. The cosmic microwave background radiation. This is the oldest light we can see in the universe in any direction we look. This is really the afterglow of the Big Bang, this thing up here. Of course, it had to make another appearance. And we can actually put bounds on the amount of cosmic strings that could be in the universe based on the fact that we did not find any within the CMB. So if you had cosmic strings, you would expect to see not directly the string itself, but some residue effect of the strings within the CMB. Because we don't see any, we can put constraints on how many cosmic strings there could be. So cosmic strings are tightly bound by the CMB and also now by LIGO as well, because LIGO has also not found, LIGO is this detector that's looking for larger gravitational waves, like the ones from supermassive black holes. And that also puts constraints on a really big upper bound on cosmic strings, because LIGO also did not find any cosmic strings. But that doesn't mean they're not there. So could LISA detect cosmic strings? Question for you, Anna.
Yes, Lisa could. The frequency range is the correct one. So, based on the current knowledge, yes, the answer is yes. But of course, then it is bound, depending a bit which model you use, because there are multiple models. And I believe the Nanograv one, so the pulsar timing array one, uses the number Goto model, and that is that kind of gives quite like strict bounds on the string tension. So the string has a tension, so do cosmic strings. So it is kind of tightly bound at the moment from the pulsar timing arrays and from the CMB, as Diana mentioned. So we will see what happens in the future.
But it is a very, very fun topic. And as David was saying here in the comments, are we talking about the pulsar timing array? We are indeed. And I know this topic has been requested. It is on my list. I have a list of topics to go in depth one day, and the pulsar timing array is on the list. I know Abyss has requested it multiple times. So consider this today just a teaser when I actually get round to going fully in depth on that topic. And yeah, we've I've been ignoring the comments. Sorry about that. I know there's a backlog of questions to answer now. No one said there would be cosmic strings. Well, I actually announced it. I specifically announced on Twitter that there would be cosmic strings today. So we did. And when were cosmic strings first proposed? Do you remember?
Oh, it's by Kibble in 70s, I
1970s.
believe. 70s, I believe. I
Okay,
can
yeah.
actually quickly check that because I have written it down in like
Nice.
ages
I
ago.
remember the century. I'm happy if I
Yeah,
remember the
it
century. I'm
is.
so
It
bad with
is in the
dates.
70s. I have not written the
Nice.
year, but 70s roughly, and they have been quite thoroughly researched after that. And there is still
Yeah.
interest in the cosmic strings research. It's not. it's not going anywhere. There are new exciting things coming and going, as it is
Yeah,
with science.
new models, new ways of detecting
Yes.
them, new signals that we could hope for. Occasionally we get hints where people are like, is that a cosmic string? And then it turns out, no, it wasn't, but it's still
Yeah.
interesting. There's an excellent question by James, or there was an excellent question by James some time ago. Can you exist inside the strings, or could anything exist inside the strings?
Well, I hope not. They are quite dense. So I don't see how anything how anything could exist inside them. There are, of course, like different models. For example, you can have cosmic strings that have monopoles, like magnetic monopoles, that have formed. So you first have magnetic monopoles forming, and then you have cosmic strings that kind of thread them and form these like necklace structures. So it's the magnetic monopoles are kind of the beads in the necklace. So
I just remember you did send me a video for
I
this.
did. There is the decay of a cosmic string and magnetic monopole network
Is
forming.
is this the
This
one we
one.
want? Yes.
Yes, that is exactly the
Okay.
one.
It's
When
just
it
loading.
loads. Yeah, so the
Yes.
orange ones are the magnetic monopoles and the green ones are cosmic strings.
So this is a simulation of what could have happened if you had a bunch of cosmic strings in a box.
Yes, in one specific theory.
Yes. Yes, we
I
should
should
always
I should
mention as
mention that that is a very specific, like of a model. So
so yeah, these worms that you see moving through space, these are cosmic necklaces, so just really big cosmic strings. And
yes,
there's a bunch of cool videos for this. There's another one you sent me as well, which is also very similar. But yeah,
yes,
you get the idea. You can have these cool things in the universe. And let me just stop presenting that one. Okay. There were a few comments I wanted to address, and we keep getting distracted. But let me just go back to some of the comments here, because it's very easy to get carried away on one topic and
yes,
then we forget. So going back to where I left the comments off, there was a question by James quite some time ago. With the creation of the universe, are there great voids that exist unusual or unexpected? Just to very briefly mention, those are completely expected. We have this cosmic structure in the universe, this cosmic web, where you have voids and you have superclusters. This is completely expected. And I'm just answering that one briefly because it's very off topic for today. But these great voids are expected. There are still people studying just how expected they are and what's happening there, but they are relatively understood. Okay, then there was me freaking out about the frozen sea. There's a question from Reddit, what was before the Big Bang? We already answered that before, that's basically something we cannot answer. So skipping that question, sorry. It's out beyond the scope of this stream. We can do like in papers, that is left for future work. There's an interesting question here, slightly off topic. In your opinion, which scientific concept which was later disproved that did the most amount of damage to the development of that area of study? Now, I think that's an interesting question, and it just emphasizes the way science works, right? We try things. Sometimes we're right, sometimes we're wrong. If we're wrong, we go back to the drawing board. This is how it works. Now, I don't think that there's anything that has been extremely detrimental to the field because this is how the field progresses. We could think of different things. At some point, there was an announcement of neutrinos traveling faster than the speed of light. Turned out to be wrong. This is fine. At some point, it was announced that we'd found primordial gravitational waves. Turns out there was dust in the way. It's just part of the scientific process. I don't think anything of this is like detrimental to how we progress with science. It's just part of the process. Admitting that we're wrong, it's not easy, but it is part of the scientific process, and it just helps us gain more knowledge. So I think it's an interesting question, but I don't think I can point to something specific there. If you have more thoughts on that, Anna, feel free to jump in.
Well, I completely agree with you. That is how science is done. We will make mistakes. We will chase after something that is not actually there. That happens. We are humans doing science. You can't remove that fact from the science. We are biased creatures.
Yeah, that's the thing, that science is always going to be human influence, which is why science is also always going to be political. But I'm saving that rant for another day. David Dunn here in the comment. So David Dunn is an astronomy professor, so he's very good at fact checking what we're saying. And he mentions here that the pulsar timing array is active in Australia, Europe, and North America. So Europe was the one we weren't sure about. Okay, going through the questions. There was a comment by Paul because you mentioned a bachelor thesis. So I know the system works differently in different countries. So the bachelor is the equivalent of the undergrad in the US.
Mm,
And I'm not sure if in the US there is a bachelor thesis, but in most of Europe there is. So you did yours on cosmic strings.
yes, I did.
So I
Base.
did my bachelor thesis on exoplanets, which was super fun. I actually
Oh
got telescope
wow!
time to observe
What
stuff.
really? Oh, I'm
It
so
was so
jealous
fun.
now.
It was amazing. We thought we'd found a transiting planet. Turns out there was an eclipsing binary in the background that was messing up our data. Whoops. But it was fun. I spent like 1 year working on the bachelor thesis, even though it's supposed to be in Spain, it's supposed to be 6 months. Here, I think it's closer to 3, 4 months. It very much
Something like
depends on
that,
the
yeah.
country. But it's very nice. It's a way to give undergrads a first taste of research or a first really in-depth topic. Most countries in Europe do have that. So you have a bachelor thesis. If you do a master's, you have a master thesis. And if you do a PhD, then of course you have your dissertation. What did you do your master's thesis on?
So I did that on bubble nucleation on the Electroweak phase transition. So trying to basically calculate how quickly the bubbles are nucleated after the phase transition, or during it, kind of how depends how you look at it.
Yeah. So there was, but yeah, bachelor thesis, master thesis, they are very important parts of becoming a scientist. I believe. I think they're super useful. I learned a lot with my bachelor thesis and with my master thesis. My master thesis was on inflation. It was really fun, and it got me involved in the Planck mission, which I was incredibly happy about. I was on the Planck inflation paper thanks to my master thesis, and that still seems completely surreal to me.
Oh wow!
We have an excellent comment from Paul here. Going, and it's a bit delayed because of me trying to catch up with the comments. When you were talking about cosmic strings, you used the word dense. Paul is saying here, if we can use a word like dense, how can it be one-dimensional?
Not sure if I'm able to actually answer this in a way that makes sense.
I think that's a great question, and I can find a way of answering that in a nice way. So no,
Please do.
I'm at a blank here.
um, yeah, I'm not sure if I can actually answer that from the top of my head. It has to do how they. Well, it depends a bit, I suppose. I'm
So
sorry, I
so
cannot give you one like straight answer on this.
it's an excellent question. I think, and really don't quote me on this because this is just pulling some random facts out of my brain here. When we talk about density, we're often more concerned about the energy of something
Yes.
and not so much about the mass per volume. So you can have something that is one dimensional but contains a lot of energy. We would say that's very dense, but that doesn't necessarily mean that it's going to sink if you put it in water. It's just that it has a lot of energy contained in a one-dimensional space. I think. I'm not sure if that makes sense. That somewhat makes sense to me, but
Yes, I mean that does make sense. Yes, they are. There's a lot of energy in them, or so in that sense they are dense. Yes, but I cannot give you a straight answer how the mass aspect relates to this directly in this case.
it is a great question, Paul. Really nice question. And I'm amused because at some point Scott made the comment of scientists baffled, probably when we were talking about how science progresses. But that's very much what we are now. Scientists are baffled by question about density of cosmic strings. But yeah, that is a great question. I love when questions stump us because now I'm going to go try to figure that out later today. Like I love it when you guys all ask or you people ask questions that we can't answer. That is what makes this so fun. Absolutely love it. No bachelor thesis in the US, but you did a master's thesis and a PhD. Nice, nice, very nice. So we are already at 1 hour stream time. So this is usually when we start wrapping up. So Anna, is there anything else you want to talk about that we might not have had time to cover yet? So we've got done cosmic strings, phase transitions, gravitational waves. Is there anything else you want to tell us about?
I think that's pretty much it for today. At least I can't think anything else that I would like to discuss today. No.
Now, I think we covered a lot of stuff, and again, a lot of what we're talking about is stuff that happens in the first second of the universe. So I asked early on in the stream, like, what could possibly happen in 1 second, and now we spent an hour talking about stuff that can happen in that first second, and we're barely scratching the surface of everything that can happen in this first second of the universe. So we already mentioned before that you are an artist. You have your blending stuff on YouTube. Is there anywhere else people can follow you if they want to stay up to date with your work, or maybe any social media you want to share?
So yes, you can find me on Twitter at Anna Kormo, so my name, which you can probably read somewhere on the screen, I suppose.
Yeah.
Hopefully.
But yeah, if you go to my Twitter feed, DCHooper91, my latest post or one of my latest posts has a link to Anna as well. So easy to find. You have less than 1 minute left on Reddit. Yeah. Yeah, it's already an hour, right? Wow, we've already been going for an hour. So how long was that second in time dilation? Yeah, this is a fun question that we just take on Earth second, because if we had to factor in time dilation in the early universe, things get messy.
Yeah, and physicists usually speak in terms of energy or temperature in these kind of scales anyway, so these
Or
seconds,
redshift.
yeah, the seconds are more there for that people can actually understand roughly when they happen.
Yeah, but it's much more common to refer to things in terms of their energy. Just comment here of thank you, David, for sharing the Cup of Cosmology webpage. So if you like this show, if you're enjoying what you're hearing here, follow Cup of Cosmology. If you can go to cupofcosmology.com, new webpage launched a week ago. And I should make a comment there that I meant to make already. Last week, I announced my new email address as well, contact@cupofcosmology.com. And due to a slight technical issue, being that I messed up my DNS server settings, for the first about 12 hours, if anyone sent an email to contact@cupofcosmology.com, it didn't come through. It's completely on me. Unfortunately, I know an IT person who fixed it for me or told me how to fix it. If you sent me an email to contact@cupofcosmology within the first 12 hours so between Sunday and Monday last week, it didn't come through, so please send it again. Everything from Monday morning onwards is coming through. So it's just a 12-hour gap. Sorry about that. I apparently messed up my DNS. So yeah, check out cupofcosmology.com. You can find the links to the stream. Next week, I'll be on same time as today, and next week we're going to be talking about rogue black holes and the new discovery of a rogue black hole. I'm super excited for that, and I'm going to have to do my homework for that stream.
Oh, that's really exciting.
It's going to be fun. So, Anna, thank you so much for joining. It's been really, really, really great to have you here. Very knowledgeable, lots of cool stuff.
Thank you for the invitation. It was really great to be here.
You're getting a lot of nice comments here in the comments as well. A lot of people happy to have you here. Hopefully someday you'll come back. There's always an open invitation to come back. And I won't pressure you on screen to answer that question, but if you want to come back in the future, you will be most welcome to do so.
If I have any new topics to discuss about, the research takes quite some time.
That's a problem, that sometimes research is slow, but if people want to hear more about cosmic strings or hear about cosmic strings again, or phase transitions or everything cool happening, or if you have a new animation you want to explain to us,
Oh, there will be a new animation actually.
Okay.
Of the Hals-Taylor binary will be coming to my
Nice.
YouTube channel at some point when I get it rendered.
So someone is pointing out here cosmic strings is a 5-episode topic. Yeah, at
Yes.
least we need several episodes for all of these things. Like Electroweak phase transition, we could spend hours talking about. I do have more guests in the future on my list of like maybe potential guests who might go more in detail on some of these topics. Have to see. I can't confirm anybody just yet, but I do have some more guests in the pipeline. So yeah, remember to follow Cosmo Blend, the best coffee or the best blended stuff on YouTube. That's Cosmo Blend. Also, Cup of Cosmology subscribes to that account on YouTube, so you should be able to find it there. So yeah, I'll be back next Sunday, same time as today, and we'll be talking about rogue black holes. So I hope to see you all again then, and I hope in the meantime you'll stay safe and take care of each other. Thanks for joining, Anna, and thanks to everyone in